Our first talk will be from Ephraim Gao, who's a grad student at the Washington University in St. Louis. Did his undergraduate degrees in physics and then started doing astrophysics research with Hendrik Kopczynski at WashU. And in that time, in the last 5 or 6 years, has great breadth of research in terms of some theoretical experience, some data analysis, as well as some experimental experience. And today we'll be talking about one of those experimental projects, which is the Excalibur Suborbital Balloon mission. So Ephraim, please go ahead and share your screen and take it away.
Great, and just checking that you can still hear me okay. Great, okay. Let's see. Make sure I should share everything properly. PowerPoint. Okay. Play from start. Okay, yeah, thanks very much. Just as was mentioned, I'll be sharing a bit today about our most recent Excalibur flight, as well as the design of the instrument and the data that we took last summer. So this background picture of this title slide is a picture that I took of Excalibur during one of our integration tests when we were at Esrange in northern Sweden. As you can probably guess, Excalibur is a balloon-borne mission, and our main goal is to investigate hard X-ray polarization. And we did so from the Crab and Cygnus X1 last summer. And before I fully start, I just want to throw up this list of our collaborators, spanning many institutions in the US, in Sweden, and in Japan. And they've all been vital members, one could say, instrumental in making this telescope a reality. There's really just so many moving parts to this mission, and really it takes everyone's expertise to make this happen. So to start off with the big picture, why does Excalibur care about the polarization of hard X-rays? To the timing, spectral, and imaging data that's already present from other hard X-ray telescopes, we wish to add polarization because measuring polarization is especially important when there is a preferred direction in the physical processes involved, such as the presence of a magnetic field or structures such as black hole coronae being extended in certain directions, breaking the symmetry of emission. Polarization is also helpful for giving information about sources that are too small or too compact to spatially resolve otherwise, such as the regions on a neutron star surface. Until now, the best results for hard X-ray polarimetry for these two sources, for Crab and Cygnus X1, have been from POGO, which was another balloon-borne mission that also launched from Sweden about 10 years ago. For soft X-ray polarimetry, I'm sure you all know about IXPE, the Imaging X-ray Polarimetry Explorer, which was launched in 2021, looking at the soft X-rays from 2 to 8 keV. So Excalibur, our mission, is the perfect complement to IXPE because it's looking at the hard X-rays, our range is from 15 to 60 keV or so. So now on to the actual design of our instrument. Here's what Excalibur looks like schematically. On the left here, hope you can see my cursor, and then on the right, a picture that I took shortly after launch. So Excalibur has a 12-meter long truss that's dictated by the focal length of the X-ray mirror at the front here that focuses photons down the length of the truss until they hit the detector assembly on the other end. And then Excalibur is pointed very precisely at the desired sources with the Wallops Arc-Second pointer from NASA's Wallops Flight Facility. The pointing systems are housed on the gondola, which is indicated in the center, and the gondola is also how the balloon holds up the telescope. Now I'll describe each part of the instrument in a bit more detail. So, okay, the truss again. Here's a schematic of the truss, holding it all together. It has 3 parts. There's the part for the mirror, for the gondola in the center, and then for the detector. And there's also the honeycomb structures at each end of the truss that are responsible for holding the mirror and the detector. Here's another view of Excalibur sitting in one of the hangars at Esrange, Sweden, while we were waiting to be launched, and then with one sitting PI depicted for scale. Next, the mirror that we use is a spare Hitomi mirror. The mirror had been tested and checked for alignment with our detector, set up multiple times prior to launch by our mirror experts from many Japanese institutions. This mirror has also allowed us to go from kind of first generation polarimetry, non-focusing such as POGO. They didn't have these focusing optics, to Excalibur, which does have this focusing optics that allow us to get a much better signal to noise ratio. We also have a way to check the overall alignment of the truss, the mirror, and the detector during flight. We mounted an LED ring in front of the detector, surrounding but obviously not blocking the detector. And then there's this black back-looking camera placed in the center of the mirror that's continuously taking pictures of this LED during flight. And then our software then compares the current location of the LEDs at any given moment in time with kind of the record of where it should be in the database, and then we can calculate the offset to make sure that the truss is not misaligned, and usually it's only within 1 to 2 millimeters or so. And obviously, we've never used the camera to take pictures of anything else at all. But what goes on when photons focus from the mirror then hit the detector? So after X-rays come in to the top of the detector, or what we call the polarimeter, they scatter in the beryllium rod, low Z, low atomic number, and then they are absorbed in one of the 16 CZT or cadmium zinc telluride detectors that are surrounding the beryllium rod. So the CZTs are the high Z detectors that are meant to absorb the photons as completely as possible. There are 4 electronic boards, each with 4 CZTs, and each CZT is read out by 2 ASICs. So all of this, the CZTs, the ASICs, the beryllium rod, all of this is housed within an anti-coincidence shield assembly to further reduce the background. So the shield is made up of 2 BGO, bismuth, germanium BGO, forget the exact oxide exact name, but 2 BGO crystals, one top and one bottom. They're each read out by 4 PMTs. The crystal itself is already serving as a passive shield, blocking some of the background, but then we also get the active shielding, the anti-coincidence, when we get hits in both the BGO and the CZT within a certain range of time. So if that happens, we know that the counts are not coming from where they're supposed to come in when they're focused by the mirror into the detector. So we then rule those counts out. So we have both passive shielding and active shielding with this BGO shield. To elaborate a bit further on our detection principle, so again, the photons arrive from the mirror into the detector assembly. They scatter in the low Z beryllium rod, and then they are absorbed in one of the 16 circum-adjacent CZT detectors. With 64 detector pixels in each CZT, we can precisely determine the position of the photon after it scatters. So since polarized X-rays preferentially scatter perpendicular to the direction of their polarization, there will be a significant excess of photons in certain pixel positions compared to others, and that can be visualized in something like this modulation curve here on the bottom right, which displays counts on the y-axis, and then the azimuthal angle around the beryllium rod, the x-axis. And additionally, through knowing the position of the pixel that each photon scatters into, we can also calculate the Stokes parameters. Stokes U quantifies the amount of polarization in the celestial north-south or east-west direction, for example, and Stokes U quantifies the amount in the 45-degree directions. And Stokes I is, of course, just the total number of counts. However, since X-ray polarimeters currently can't examine circular polarization, Stokes V, so we don't take that into account when we calculate the PD and the PA, the polarization degree and polarization angle. And they're given here as PD is given by this PL formula, and psi is the polarization angle. We can calculate the PD and the PA basically for each source based on the Stokes parameters. So after a lot of preparation, XL Caliber finally flew this past summer. We launched from Esrange in northern Sweden here, following this green flight path roughly until Nunavut, Canada, and then that's where we terminated the flight. It was around a 5-day flight or so. It was split between observations of the Crab, Nebula and Pulsar, and the black hole binary Cygnus X1. So in terms of our time on the Crab, we had about 50 kiloseconds of on-source time with about 56,000 events, and then 17 kiloseconds of off-source time with about 6,000 events. And likewise for Cygnus X1, we also had about 70 kiloseconds of on-source time with about 48 kiloseconds of off-source time. And then also listed below are the MDP99s, or the minimum detectable polarizations at 99% confidence for both sources. So first looking at the Crab results, we saw a clear signal excess as expected between 15 to 60 keV. The figure in the top left, this is a very rough pre-RMF corrected spectrum. Next, in the light curve on the bottom, we have on average rates of about 1.1 hertz for on-source and about 1/3 of a hertz for background, so it's a clear high signal-to-noise ratio. And in the modulation curves on the top right, we can also see the expected modulation in the signal counts with respect to azimuthal angle as expected for our source. Given that the Crab Nebula also contains the rotating pulsar, we can plot the Crab results as a function of the rotational phase of the pulsar. The phase peaks could be used to study the emission coming from the pulsar itself, whereas the off-pulse region can be used to study the surrounding nebula. So thus the PDs and the PAs detected by XL-Calibre are plotted here in the red stars and error bars for each phase interval, as well as for our overall phase integrated measurements. They were calculated, as discussed before, through the Stokes parameters just mentioned, as well as through a Bayesian analysis. On the whole, for our phase integrated results, we have a detection of high statistical significance, around 8.5 sigma or so. Detection of linear polarization was around 25% at an angle of 130 degrees east of celestial north. But given the challenges of trying to do phase resolved polarimetry, because we're taking time and phase cuts, and thus you get smaller counts, fewer counts, and worse statistics, you can see that the errors are manifestly worse for these phase regions, especially for the peaks. To reiterate, we compare our overall PDs and PAs with the PDs and PAs obtained from previous missions in the X-rays and gamma rays. On the left, we see how XL-Calibre in the red improves upon, again, the precision of the previous hard X-ray mission, polarimetry mission, POCO. On the right, we compare the PA that we find, once again in red, with the PAs for various regions that are detected by IXPE in the orange, yellow, and green arrows, as well as with the overall pulsar spin axis of the nebula, given by the dash dotted line on the right. However, as you can see in this figure on the right, there seems to be some kind of difference between the soft and the hard X-ray PAs. And why might this be? So as found by NuSTAR, the observed spatial extent of the crab seems to become smaller at higher energies. And also these various results from IXPE, these orange, yellow, green arrows seem to indicate that the PAs are becoming more aligned to the pulsar spin axis when we are looking at smaller regions encompassing the nebula. So taken together, these results seem to indicate that the higher the energy, the closer we are probing to the inner torus, or the innermost regions of the nebula, such that the XL-Calibre result, with being at a higher energy than IXPE, has the PA that's most consistent with the pulsar spin axis and the smallest IXPE region here. So energy dependence is kind of another way to explore maybe various spatial extents of the nebula, once again showing how important it is to look at X-ray polarization from the crab and other sources across this broad band of soft and hard X-rays. For Cygnus, just as we had a light curve, for the crab, we also have one for Cygnus X1. Once again, there's a clear detection of signal over background. However, even though the analysis for the source is hopefully getting closer to the end, we unfortunately don't yet have final proclamations on our PD or PA for Cygnus in the hard X-ray. So we don't yet have conclusions of what that might mean for coronal models. If you remember, IXPE detected a clear increase in the polarization degree in the soft X-rays, and then how well or not well our result fits with that will maybe provide further information on which models are allowed or not. In conclusion, so XL-Calibre combines precision pointing, the large Hitomi spare X-ray mirror, as well as a well-shielded scattering polarimeter to achieve some of the best possible performance on a balloon flight. For the crab, XL-Calibre measured a polarization degree that was a very high statistical significance, around 8.5 sigma or so, and a PD alignment that's aligned with the innermost part of the nebula. The paper for that should be coming out soon. For Cygnus X1, the results analysis are ongoing, and for both sources, we anticipate having follow-up papers with refined analysis techniques. And we also plan to release the data, spectral polarimetric data on HESARC soon. Looking into the future, flying as soon as possible from Antarctica, would give a flight that's much longer than we could get from the Northern Hemisphere, would open up hard X-ray polarimetry for the Southern Hemisphere. And then flying as soon as possible would also allow us to take advantage of the time that we still have synergy with these other polarimetry missions in the X-rays and gamma rays, whether that's IXPE currently flying or proposed missions such as Red Sox or soon to be launched missions such as COSI. Yeah, once again, we emphasize how important it is to take X-ray polarimetry measurements across the X-ray band. Yeah, thanks very much. Happy to try to answer any questions.
All right, thank you, Ephraim. Very nice talk and very cool mission. So for folks who want to ask questions, you can put them in the chat. We'll monitor the chat, and you can also use the raise hand function. And then when we see your hand pop up, we can call on you there. So we have a couple minutes for any questions for Ephraim. Maybe just to start, Ephraim, you got what I was curious about on your last slide here, which is kind of future plans for the mission. I see you have a little bit there, SMEX Mid-X probe concept. Is there anything more you can say there about maybe trying to convert the balloon instrument into an orbital class project?
Right. So that one, admittedly, I'm a little bit less familiar with. I know that younger members of our group have been working on this kind of combined polarimeter, trying to target both the soft and the hard X-rays in one mission. So I believe this would be a space mission to be able to get at those soft X-rays, but I don't know too much more. I think they have explored various techniques for what kinds of detection they want to use at the lower and the higher X-ray energies. Yeah, so I think those are some of the plans for younger members of our group.
And sorry if I missed this, are the 27, 28 flights there for XL Caliber, are those funded, already planned, or is that what you'd like to be able to do?
That, I think I'll say that's what we'd like to be able to do.
Okay, nice.
We are hopefully hopeful.
Yeah. Good luck. There's a question in the chat when you talk about flying as soon as possible. What does as soon as possible mean there?
So again, I guess there's kind of various funding news and changes coming in all the time. So I think ideally we had hoped for flying, say, December 2026. That doesn't sound like that's very possible from McMurdo. So hopefully 27 or whichever season from McMurdo would allow us to kind of fly the soonest would be ideal.
Yeah. So as soon as flight opportunities allow.
Right.
Yeah.
Yeah, from Antarctica. Yeah.
Great. All right. Any final questions for Ephraim? Okay, well then thank you again, Ephraim. Very nice job. We'll go ahead and move on to our next speaker. So our second speaker today is Itai Linial, who's did his PhD in 2022 at the Hebrew University of Jerusalem with Raheem Sari, and then earned both a Rothschild Fellowship and an IAU Gruber Foundation Prize, and has since been a postdoc at the Institute for Advanced Study at Princeton and at Columbia University. Itai is interested in a wide range of astrophysical phenomena as well as stellar dynamics. And in fact, today we'll be talking to us a bit about star-disk interactions and quasi-periodic eruptions. So, Itai, go ahead with your screen share and take us away.
All right. Okay, can you hear me all right?
Yeah, sounds good.
Okay. Right. So yeah, thank you for this opportunity. I'll be talking today about some recent work on a new class of transients we see in galactic nuclei called quasi-periodic eruptions, and a theoretical model that we have to explain this phenomenon. So just as a broader context, we're thinking here about processes happening in centers of galaxies around supermassive black holes, and interested in things happening in what we call the radius of influence. So this is where the supermassive black hole dominates the gravitational potential. So stars follow roughly Keplerian orbit around it. We have about 1 million to 1 billion stars within this volume. So it's this high density of stars in the presence of a supermassive black hole that can produce all sorts of interesting dynamical processes where stars are brought into precarious orbits around the supermassive black hole. So some kind of schematic examples include, for instance, tidal disruption events where stars approach the supermassive black hole on a nearly radial orbit, penetrating the tidal radius and being split apart by tides. We may have EMRIs, extreme mass ratio inspirals, so either compact objects or stars inspiraling towards the supermassive black hole by the emission of gravitational waves. I'll be talking today about quasi-periodic eruptions, which we think are related to stars on tight orbits around the supermassive black hole, possibly interacting with accretion disks. And other related phenomena include the Hills mechanism, where binaries get split apart by tides. One star gets ejected as a hypervelocity star, and the other star remains bound on a tight eccentric orbit. And stars might also undergo direct physical collisions because of the high density of stars. These are kind of the processes that we try to understand, and we want to understand what would be their observational signatures in different messengers. Moving to observations, so up until a few years ago, we had this sense of the zoo of variability seen from galactic nuclei, usually associated with active galactic nuclei, so supermassive black holes accreting large amounts of gas. And this sort of variability has been seen over different timescales and in different bands. And these are a couple of examples of what this variability might look like. And then in 2019, there was a new discovery of this class of quasi-periodic eruptions, which are seen as these repeating X-ray flares, very regular, very high amplitude, seen in centers of a few nearby galaxies. So just to give you a few more details about what QPEs are. So to date, there are about a dozen confirmed sources with maybe a couple more good candidates. The flares are seen in soft X-rays, and they repeat every couple of hours to maybe a couple of days. The duty cycle, so the duration of the flare relative to the time between flares, is about 10% or so. They reach luminosities of 10 to the 42 ergs per second, maybe even more. And their corresponding black body temperature is roughly of 100 or 200 electron volts. And they seem to occur around supermassive black holes of relatively low mass, around 10 to the 6 solar mass. This is a more detailed view of how the flares actually look like. So in between the flares, we were seeing this quiescent soft X-ray emission, and then the flares rise and fall, and you can see the behavior in different bands. So they rise more rapidly in the harder bands and also fall more rapidly. Here you can see the evolution across the transition from quiescence to the peak of the flare back to quiescence, showing here the spectrum evolving from this soft quasi-black body emission, increasing in temperature and luminosity to the flare spectrum. It's also worth mentioning that they actually have this interesting hysteresis loop where the rise is harder than the decay, showing here the evolution in luminosity versus temperature diagram. Okay, a few interesting clues about the nature of these QPEs is that at least in a couple of sources, we see this regular behavior where the quasi-periodicity is actually regular in the sense that the time between flares alternates back and forth between slightly shorter, slightly longer flares. So say 9 hours, 10 hours, 9 hours, and so on. And you can see this showing the time between consecutive flares alternating back and forth in a couple of these sources. Also, when you stack up the light curve in the sum of this long and short recurrence time, you can see that the light curve stacks up nicely in some of the sources, whereas other sources show this more erratic timing without this property of regular timing. Another interesting clue is that at least up until a few months ago, there has been some tentative association between QPEs and TDEs, tidal disruption events. So at least in a couple of sources, before QPEs have been first observed, there was a gradual long duration decay in the quiescent X-ray flux seen before QPEs first appeared. This is, for example, in the first system that was observed, GSN 069. Over the course of a decade, we've seen this gradual decay in X-rays, and then QPEs appeared. Same in another source. There's also some evidence that the hosts of QPEs tend to be consistent with the host galaxies of TDEs. So there's been some evidence with regards to that. What is the origin of these QPEs? So there have been many different models that have been suggested, and I would say this is kind of a zeroth order checklist that any model should be able to explain. Some of the properties related to their timing, their emission, and some of the associated properties. And I highlighted what I think are kind of the key clues to this mystery. This is a broad classification of the different models that have been proposed, and we are definitely at this stage where the number of models exceeds the number of sources. Broadly speaking, we're talking about models involving some sort of disk instability, producing these recurring flares. And the other class, which I'll be talking about, is a supermassive black hole with some orbiter around it that is essentially related to some orbital phenomena in explaining these recurring flares. And I'll focus on this class of models involving an orbiter interacting with a disk around the supermassive black hole. So this is a cartoon showing the basic idea that we proposed about 1.5 years ago, which involves a supermassive black hole surrounded by some compact accretion disk. Around it, we have what we call a stellar emery, so a main sequence star on a tight orbit around the supermassive black hole, highly inclined with respect to the disk. And this star collides with the disk twice per orbit. In our model, the flares are produced by the collisions between the star and the disk, and the quiescent emission seen between the flares is originating from the inner part of this radiative disk. So the timing of the flares will generally be subject to the precession of the orbit, possibly the disk, and I'll also comment on the association between TDEs and QPEs within this picture. So one thing that we can naturally explain with this framework is this regular timing behavior where the recurrence time alternates back and forth. So if the orbit is slightly eccentric, then the time between consecutive flares will be shorter when you pass through pericenter and slightly longer when you pass through apocenter. And to explain these deviations that we are seeing that are of order 10% or so, that corresponds to an eccentricity of roughly 0.1. And actually, from the dynamical formation picture that we have for this system, this is actually favored. What happens during the collisions? So the star sweeps up this cylinder of disk material. There's not much gravitational focusing because the collision is so supersonic with respect to the sound speed of gas in the disk, also with respect to the escape velocity from the star. So it's essentially set by the geometrical cross-section of the star. Assuming something about the disk, it being a radiation-dominated thin disk, we can estimate what is the amount of mass being swept, what is the initial energy budget in this shock-heated disk material. The velocities we're talking about, since the periodicities are of order hours, are roughly 0.1 c. We recently conducted some simulations, some radiation hydrodynamic simulations of this process of a star plowing through a disk. You can see that you can actually produce these two plumes, one going in the forward direction. Here the star is actually going downwards with respect to the disk, and one that is ejected backwards. This is due to the pressure gradient that is generated within this shock-heated disk material searching for a path of least resistance. So how radiation is produced? So initially this shock-heated disk material is very optically thick, so it has to expand quite a bit before it can radiate. The condition for the radiation to escape is that the diffusion time of photons will be similar to the expansion dynamical time of this ejecta. That sets a criterion on the optical depth. It needs to go down to about 10 or so, accounting for the decay in optical depth and the degradation in internal energy due to the adiabatic expansion. One can estimate what is the luminosity that you get from this sort of interaction, roughly in the right ballpark of about 10 to the 42 ergs per second. The duration of the flare within this picture is set by the photon diffusion time. You get something of the order of fraction of an hour. The flare temperature is actually determined by the photon production processes as the star plows through the disk. Turns out that the emission is not completely thermalized, but it's actually, in a way, a Comptonized free emission set by the finite time it takes the star to plow through the disk. And we get temperatures that of order 100 electron volts. And recently, we conducted some numerical studies on this process, doing Monte Carlo radiative transport calculations, where we follow the photon production processes in the shock ahead of the star and calculating the resulting emission as this cloud of ejecta expands above and below the plane of the disk. And we're able to reproduce, at least qualitatively, the salient features of these flares, showing here the emission in different bands, the fast rise and fast decay in the harder bands, and also this hysteresis loop that I've mentioned. What is the origin of the disk in our model? So there are a few options. One in which the disk is fed by the star itself, if the star is undergoing Roche-Lobe overflow. The alternative is that this is an extended AGN accretion disk. And the third option, which we opt for, is that this disk is actually produced by the TDE of another star that was disrupted in that system. This has led us to this picture that an MRI plus TDE equals QPE. And the basic argument is quite simple. If you think about a star orbiting the supermassive black hole at a separation required to explain the periodicities that we're seeing, in vacuum, it will stay there for about 1 million years. That's roughly the gravitational wave timescale at these separations. If you account for the rate of TDEs in galactic nuclei, which is about 1 TDE per 10 to the 4 to 10 to the 5 years, almost inevitably, this MRI will interact with a TDE during that time. So a second star will happen to pass close to the supermassive black hole, be disrupted, produce a TDE, and eventually settle onto a thin disk. And then the MRI that was already there will now collide with the disk and produce these flares. So this naturally explains the periodicities that we're seeing, because if you think about the orbital period at roughly the tidal radius, which is where these collisions would occur, that is identical up to a factor of order unity to the dynamical time of the star, which is of order hours. So we predicted that a significant fraction, maybe 1 to 10% of TDE flares should host QPE. That was the prediction that we made about 1.5 years ago. Interestingly, several months ago, around April, this result came out. So the TDE AT 2019 QIZ was run-of-the-mill TDE observed in optical, showed a typical rise and decay following T to the -5/3. It has been followed up in the last couple of years, demonstrating this typical late time TDE emission that is consistent with gradually viscously spreading and cooling accretion disk. You can see here this typical UV optical plateau and this gradual decay in X-rays. Nothing unusual about this source. And then some additional observations to study the TDE disk show this interesting brightening of the source. And then with additional X-ray observations over the course of 10 days with NICER, this light curve came out. So we detected QPEs in the aftermath of a TDE consistent with the theoretical prediction. Another interesting aspect is that independently of these QPEs from the late time TDE observations, one could fit a disk model. And it actually turns out that the outer edge of the disk, shown here, the surface density is a function of radius, is consistent with the separation at which this orbiter should be to produce the periodicity that we were seeing. So this is the line showing where the orbiter should be to explain repeating flares once every 2 days or so. That has some interesting consequences because it means that now we can detect potentially many more QPEs by repeating the same exercise, doing follow-up X-ray observations of TDEs that have happened in the last couple of years and look for these repeating X-ray flares. Yeah.
Can you try to finish up in about 1 minute or so?
Yeah, this is essentially the last slide.
Okay.
So I've mentioned these two channels where stars could be destroyed in galactic nuclei. There are also some interesting consequences for millihertz gravitational waves. And I'll just finish with this summary slide and take questions.
All right, thank you. Sorry, I jumped in there. You were wrapping up already. Appreciate it.
Sure.
Okay, again, feel free to use the raise hand function or drop a question in the chat. We actually do have a question in the chat right now from Hugh Hudson. In the star disk interaction, is there any role for a magnetic field?
Potentially. We're still at the stage where we're trying to get the basic components right. I'm not sure if there's inherently some important role for magnetic fields, but people have been looking into interactions with accretion, with magnetized accretion disks, finding interesting results about outflows and so on. But I'm not aware of any crucial component that is needed to explain the QPE observations.
All right, thanks. We do have another question in the chat. For the person that posted that, if you'd like to unmute yourself, you could ask. Otherwise, I can read, but feel free to unmute. It's a little longer of a question.
It's me. Yeah, the AMRI event and the schematic, your cartoon diagram remind me of the BE transients, which have a circumstellar disk and neutron star in a centric orbit. Those exhibit a wide variety of phenomenology in terms of the amplitudes and time profiles of the outbursts. Sometimes the outbursts are absent. Sometimes they're super outbursts or something like that. Do you anticipate that type of variety in the phenomenology we expect in the EMRIs?
Yeah, so with these QPEs, the more we study them, the more rich phenomenology we find. For example, I've mentioned how some sources show this more erratic flare timing, which is not explained by a simple eccentric orbit interacting with a planar disk. So some of the ideas that have been proposed is that if you actually account for, say, the disk precession, rigid precession, and the apsidal and possibly nodal precession of the orbiter, that could perhaps explain this richer phenomenology. And I'm actually thinking that what might be important is that as this star repeatedly collides with the disk, some stellar material gets stripped apart, ablated by the strong ramp pressure that the star experiences. And this stellar debris can then form these more elongated stream-like structures that could slam into the disk and produce these more complicated flare structures. So I think there's still a lot of interesting puzzles with potential clues in this context. And yeah, I think that's kind of my answer to that question.
All right, thanks, Itai. With that, we'll go ahead and move on to our next speaker. Thank you again. And our final speaker today will be Steve DeKirby. Steve got his start as an RU actually at Fermilab doing experimental astrophysics, and then went on to earn his PhD from the Department of Astronomy and Astrophysics at Penn State, working with Abe Falcone. And Steve is now a postdoc at Michigan State University and is also a member of the IceCube collaboration. So Steve's work primarily focuses on X-ray and gamma ray analyses of extreme galactic systems that might produce high-energy neutrino emission. So Steve, with that, go ahead and feel free to share your screen and begin.
Yeah, thank you very much. Let me just share my screen real quick. Do you see this okay?
Yep, screen share looks good.
Great, thank you. Thanks for the introduction, Drew. Like you mentioned, I'm currently a postdoc at Michigan State University and a member of the IceCube collaboration. For my talk today, I'm going to talk about some work that I've done in several major projects over the past few years, focusing on the Fermi unassociated gamma ray sources and how studying these unassociated sources can help paint a more complete picture of the high energy sky. So to start off, just a little background, which to many people here will probably just be very familiar. In its 15-year history, the Fermi Space Telescope has dramatically expanded our understanding of the high energy sky. And conducting its all-sky survey in that time, it's built out a substantial catalog of gamma ray point sources, investigating high energy systems throughout the universe. Now, these point sources include extragalactic blazars, galactic pulsars, other local high energy objects. In its most recent data release, the Fermilab Point Source Catalog for FGL-DR4 contains almost 7,200 individual gamma ray point sources, and it's the state of the art of our understanding of the GeV sky. These point sources go down to a flux limit of about 10 to the minus 12 ergs per second per centimeter squared. That'll be relevant later. And along with spectral fits, one part of the Fermi catalogs that I've used extensively in my work are the associations and identifications of these gamma ray sources with other objects in other wavelength bands. As you can see in the plot on the pie chart here on the right, the majority of the point sources that Fermi has identified are extragalactic blazars, jetted AGN viewed down the jet, but there are also a diversity of other object types. You've got some other AGN, hundreds of local pulsars, one of Fermi's most famous catalogs, as well as a smattering of other local objects as well. Notably, and this is the focus of the talk, 28% of these Fermi point sources are unassociated. That means they don't have confident cataloged association with astronomical objects in other energy ranges. These unassociated sources represent a systematic gap in our understanding of the gamma ray sky. And over the past few years, both when I was doing my PhD at Penn State and now here at Michigan State, analysis of these unassociated sources is critical to understanding the gamma ray sky and its relationship with other energy bands. So for this talk, I've kind of divided the talk in two, and I'm going to focus in the first half and in one way to follow up these unassociated targets. And in the second half, we'll talk about some current work that I and my collaborators are doing. So to start off with, I want to look backwards to when I was doing my PhD at Penn State. And the work this work was taking this sample of unassociated sources and trying to find low energy counterparts with swift follow-up, multi-wavelength follow-up. This work I did at Penn State along with my advisor, Abe Falcone. It's currently being continued by Kyle Newman, a current Penn State grad student, and a wide variety of collaborators contributed as well. So one more piece of background before we dive into the science. The Neil Gehrels Swift Observatory was launched in 2004, so it is almost old enough to drink, and its primary mission is to rapidly follow up gamma ray bursts with its 3 parallel telescopes. So Swift is actually 3 telescopes in one, which makes it an extremely powerful tool for multi-wavelength observations. The Burst Area Telescope, a hard X-ray telescope, the X-ray telescope, which observes from 0.3 to 10 keV, and finally the UV optical telescope. These last two together, XRT and UVOT, provide simultaneous coverage in a wide field of view, 22 arc minutes, which makes Swift a particularly useful observatory for following up the types of objects that can produce radiation across the electromagnetic spectrum, especially blazars, for example. Blazars, because they emit radiation from radio light all the way up to extremely high energy gamma rays, are valuable targets for follow-up with Swift because of this multi-wavelength capability. And an ongoing project led by my former advisor, Abe, at Penn State, has used Swift to try and find counterparts to unassociated sources to expand our understanding of the different classifications of gamma ray objects. So this observation has used millions of seconds of observation time with Swift over the past decade or so to try and find these counterparts. Now, this is valuable because in order to classify the previously unassociated sources, getting an optical and an X-ray flux from Swift follow-up observations is vitally important. Like I mentioned, blazars emit across the entire electromagnetic spectrum, but many pulsars, for example, are only detectable in X and gamma rays, not in optical light, which makes Swift's capabilities useful for discriminating between these different classes. Starting in 2021, then again in 2023, and with a current third catalog in the final stages of publication, Abe, me, and our other collaborators, we've been building these catalogs of detailed low-energy counterparts to Fermi sources. And in our 2023 catalog, we presented over 130 extremely likely blazar candidates at these unassociated sources, as well as a substantial population of likely pulsars as well. These identifications were made with neural network classification. I'm not going to talk about that right now, but they've been largely backed up by follow-up observations by other teams. So the unique capabilities of Swift make it a valuable tool for building our understanding of the gamma ray sources, of the unassociated sources in particular. And that's because when Swift XRT follow-up establishes a spatial localization of a likely X-ray counterpart to a gamma ray source, it allows us to go back into archival data and build a multi-wavelength SED of the unassociated source. You can see one such example here. This source was identified as a likely blazar by our neural network, and using a few arc-second spatial precision established by Swift XRT, we can build this multi-wavelength spectrum that includes radio, infrared, optical, X-ray, and gamma ray data. And this shows the nice two-hump spectrum that's characteristic of a gamma ray blazar with a low-energy synchrotron peak and then a high-energy inverse Compton or hadronic peak, if you will. With these multi-wavelength SEDs and with these new catalogs of likely counterparts to unassociated sources, we can start to answer theory questions. And in the latter half of my PhD, I used the substantial catalog of new blazars that we had found among the unassociated sources to try and see how these new blazars fit into the blazar sequence as a whole. Now, the blazar sequence is a sometimes controversial phenomenological trend among gamma ray blazars that the most luminous gamma ray blazars are FSRQs and have redder, lower energy spectra, and the dimmest blazars more likely to be BL lax and have bluer spectra, though lower luminosity. So by establishing this entirely new catalog of blazars among the unassociated sources, it provides a very elemental scientific way of investigating the blazar sequence. We have an entirely new sample of blazars, and we can see if they confirm or contradict the predictions that these new dimmer blazars should have even bluer spectra. To do this, and to investigate these unassociated sources in more detail, I used a few different approaches to try and quantify parameters of the multi-wavelength spectra of these sources. Fermi was kind of the linchpin telescope for this analysis, but with Swift follow-up, we built these multi-wavelength SEDs and measured parameters like the Compton dominance of these new blazars, the synchrotron peak frequency. And indeed, once we analyzed this sample of over 100 new blazars, we found that these new blazars have higher synchrotron peak frequency, so they seem more like high synchrotron peak BL lax than anything. You can see in the histogram here, in the center of the page, that the synchrotron peak frequency is an order of magnitude on average above the BL lax of the 4-lac catalog established among Fermi-associated sources. Indeed, looking at the entire multi-wavelength SED of these Fermi-unassociated sources compared to the canonical blazar sequence, you can see that the new blazars, they fall in between the 4th and 5th quintiles of high-energy blazars from the original 1998 paper. Establishing the blazar sequence among gamma ray blazars. So this is one way in which discoveries at the Fermi unassociated sources can expand our understanding of the different source classes that make up the gamma ray sky as a whole. With a little bit of low energy follow-up and finding a likely counterpart, multi-wavelength SEDs can be put together and then compared to existing sources to test these theories of high energy emission. So for the past few minutes, I've been focusing on the work I did at Penn State as a grad student. But now I'm going to talk about another way in which Fermi-associated sources contribute to our understanding of the high-energy sky, and that's the contribution of Fermi analysis to our understanding of very high energy and astroparticle emission. This work is ongoing as part of a wide collaboration here at Michigan State University. It's also part of my work as a member of the IceCube collaboration, the Neutrino Telescope at the South Pole. My collaborators for this include Shuo Zhang, Tulun Erjin here at Michigan State, as well as other collaborators around the country and around the world. Very briefly, as you see here in this plot, Fermi's GeV map of the sky, and especially the galactic plane, shows intriguing coincidences with the TeV map established by telescopes like HAWK or LASSO, as well as IceCube's 2023 announcement of observed neutrino flux from the galactic plane. Linking up the Fermi gamma ray emission observed in the GeV light with TeV gamma rays from HAWK or other telescopes can help us understand what sources might be producing these neutrino emissions and test models for the most energetic systems in our galaxy. The next couple slides, I'm just going to be presenting case studies of how Fermi gamma ray analysis contributes to understanding these extremely complex galactic systems. The first one I'm going to be talking about is observations near the Fermi-unassociated source J0340.4. This is in the galactic plane, and it's this Fermi-unassociated source, which is red here on this sky map, has frequently been discussed as a possible counterpart to the LASO source 0343, which is an unclassified galactic pevatron. That means it's emitting light and astroparticle emission up to 10 to the 15 electron volts. This Fermi-unassociated source has been a perennial target as a possible counterpart to this gamma ray emission. So when I and my collaborators analyzed some XMM data we just got about this source, we were testing whether there might be an X-ray counterpart in the region of this Fermi source as well. Currently other groups are working on this data in greater detail, but intriguingly, we found an X-ray pulsar wind nebula distinct from the Fermi source in the region of this LASO emission. This suggests that the contrast of this X-ray pulsar wind nebula with the Fermi source requires further analysis into seeing how they relate with this obviously complex region of high energy analysis. But without understanding this Fermi source and my collaborator Talun's contributions to this paper, our understanding of this pevatron object would certainly be substantially less detailed. Keep an eye out for some papers we published on this just in the past month, as well as some ongoing work by other collaborators. The other case study I want to talk about is the Fermi source, the Fermi-unassociated source 1902.5. This is also in the galactic plane, and some collaborators as well as HAWK collaborators are currently looking at emission in the TeV and higher ranges from HAWK and LASO sources in this region. Interestingly, radio observations have detected the presence of substantial molecular cloud distributions in this region, which suggests that this region might host the hadronic processes that could lead to neutrino emission throughout our galaxy. For this region, Fermi radiation in the GeV range connects to the TeV radiation that we observe with telescopes like HAWK and LASO in their catalogs, and can help build a multi-wavelength model to predict whether neutrino radiation from a source like this object is likely to be observed with IceCube or future telescopes. This is all very preliminary. So these past few minutes, I've just been talking about some examples of how the unassociated sources as a whole can contribute to our understanding of the high energy sky, either by being linked to low energy objects via follow-up X-ray radiation, or by contributing to our understanding of TeV or PeV sources as a broad gamma ray analysis. If I may paraphrase the famous words of Abigail Adams, who said, "Remember the ladies," I would simply say to the high energy community as a whole, remember the unassociated sources. It might require a little additional work establishing a counterpart, but when you establish that, they're just as valuable to our understanding of the gamma ray sky as the other associated Fermi sources. Thanks, and I'll be happy to take any questions you have now.
All right, thank you, Steve. Very nice talk. I especially appreciate your reference to Swift's age. I think that being old enough to drink is a very nice measuring stick for space missions.
Sure is, yeah.
Okay, any questions for Steve? Please feel free to use the chat, or again, you can use the raise hand feature and ask your question directly. Okay, Carolyn, see a hand raised from you.
Hey, Steve. Thanks for the fabulous talk. So I have a biased question. I'm coming from the MEV gamma ray world. You're talking a lot about associations between hadronic processes in the GeV, et cetera. Have you thought about what these could potentially show in the MEV range?
Yeah, that's, I think MEV gamma ray astronomy has been a sadly neglected field of observation just because there haven't been telescope capabilities. I know, like you said, there's a lot of interest from the community in this analyses. The sample I was talking about of X-ray follow-up, for example, finding an X-ray counterpart, is drawn from a sample of Fermi-unassociated sources where we just found one nice solitary X-ray counterpart. Obviously, that makes it easier to conclude an association. But for many of these targets, we find more than one X-ray source in their uncertainty ellipse. For a source like that, an MEV emission could substantially help us establish the most likely low energy counterpart by giving additional spectral and positional information. So upcoming telescopes like COSY, for example, I think will substantially increase our understanding of these unassociated sources.
Thank you.
All right, any further questions for Steve? Okay, well, with that, we can go ahead and wrap up this month's seminar. Thank you, Steve, and thank you to all three of our speakers. Very nice talks today. And again, if you want to either present yourself in future seminars or nominate someone to present, please feel free to use that nomination form. And we will be back again in a couple months with another set of speakers. Thank you, everyone.